Initial stages in the hydration of alkynes proceed very similarly to the hydration of alkenes. So if we treat an alkyne, in this case a terminal alkyne, with water, in the presence of mercury, salts, and sulfuric acid, we will get a product which looks very similarly to the product of addition of water onto alkenes. This is basically a compound known as enol or vinyl alcohol, and it's called that name because it has an OH group attached to one of the carbons of the double bond. Okay? However, what we notice is that we don't isolate this as the final product in our reaction, but instead we get a molecule of a ketone, which is what we get at the end of the day in this reaction. Let's see how does this work mechanistically. The first step here is the attack of the triple bond on alkyne onto mercury 2 salt, which gives us a vinyl cation. A pretty strange vinyl cation because it still has mercury attached, but the vinyl cation nevertheless. Now this cation is very quickly attacked by water to give us this protonated version of an enol, and a loss of proton gives us something that already looks like an enol quite a bit. Except it still has mercury attached, and this mercury is lost after protonation, where we get again a cation, and elimination of mercury from this cation will give us an enol as the final product. But the question is now, how does this enol transform itself into a ketone? And why? The reason why this transforms into a ketone is, lies in thermodynamic stability. The CO bond in ketone is stronger than that one in enol, and so the thermodynamics works out in favor of the ketone. But how does this happen mechanistically? We can understand if we understand that there is acid present in the reaction mixture still, and this acid can protonate the alkene double bond. And so now we're getting a cation, which looks like this, and the oxygen lone pair can form another resonance structure here. We have HO plus, C, H, and R here. Attack of a base onto this hydrogen can now release the hydrogen and give us minus BH and give us back the ketone in the protonated form. And this phenomenon is known as acid catalyzed for obvious reasons. Keto-enol equilibrium, also known as tautomerization. We'll see this a lot in other examples of, especially when we start talking about ketones. But it's interesting that this shows up first time when we start talking about alkynes. And to give an example of how does this actually work, if we expose this heptine to solution of mercury, salt, and sulfuric acid, then we will get this 2-heptanone in about 80% yield as a product of Markovnikov-like hydration followed by tautomerization. In the next subtopic, we'll see that the similar mechanistic principles apply to hydroboration, but again with the outcome which is anti-Markovnikov as typical in hydroboration of alkenes.